So now we are ready to tackle our first partial differential equation using separation of variables method and see how we can solve it. So let's describe the situation first and then try and understand the equation a little bit first before we try and solve it. Okay, this first equation we will be looking at is called the heat equation, which by the way is also known as the diffusion equation. Next week we're going to do diffusion equation. It's actually the same form, right? It just describes slightly different things. So this heat equation can be used to represent this physical situation of having, let's say, if you like, a metal bar, okay, a bar of a certain length, let's say L. So we have a bar like this, right, and it has a certain length L. So we place this bar on the x-axis, and let us, for convenience, place it such that one end is at x equals to 0, therefore the other end will be at x equals to L. This is along our x-axis. So imagine that this bar is just one bar and, you know, no width, no height, and so on. So it's only one dimension, one space dimension. If we say that somewhere along the bar we take a measurement of its temperature or of its heat and so on at that point, okay, we can say this quantity of heat that it has or the temperature at that point is given by U, which will depend on its position x, depend on where it is, as well as the time where this measurement is taken, the time at which this measurement is taken, okay, and the temperature U of this bar at that position x and at that time t is governed by what we call the heat conduction equation, or in short the heat equation, which is given by du dt equals to c square d2u dx square, right? And of course we know that your x is defined, let's say, between 0 and L. Okay, you ask me about the endpoints, hold that thought first, and t is bigger than 0, so you ask me what happens at t equals to 0. Hold that thought first, hold on first. Okay, so basically we are saying that the heat contained, or the heat measured, or the heat amount of heat that you, the quantity of heat, or maybe equivalently the temperature or whatever it is a heat of the bar at that point, at that time, is governed by this particular equation, okay, for x between 0 and L and t bigger than 0. And then you have a c square there, right? C square actually represent, in this case, what we call the thermal diffusivity, okay, how the heat or the temperature is diffusing or being distributed. It is a property of the bar itself. So this is what we will now call the heat equation. Now, so earlier on I mentioned, you may ask, what about x equals to 0, x equals to L, or t equals to 0? Okay, this comes on as the condition that we specify. So we will want to solve this particular equation. That means find U for x between 0 and L and t bigger than 0, given some initial condition. So the initial condition will have to be what happens when t equals to 0. So U for all x at t equals to 0. That means at time t is equals to 0, how is the heat distributed along the bar, correct? So this is like a distribution of the amount of heat or the distribution of the temperature, okay, along the bar at time t equals to 0. So we then this can be written as a function of x only, right? Because t equals to 0, no more change in t. So at that point t equals to 0, we only worry about along the bar how is the temperature or the heat distributed. Okay, and this will happen for all x. So now you see the equal sign there, x between 0 and L, including the two boundary points. Okay, now this is the initial condition. This is what we call the IC, because that is at time t equals to 0. So initially what happens, right? Then we have the boundary conditions, BC. The boundary conditions will be for all time, what is the value of u at s equals to 0, and for all time, what's the value of u at s equals to L, the two endpoints. So in other words, u at 0 for all t, and u at L for all t. Let us, for the sake of simplicity, in this particular example, set this to be 0. That means at the two endpoints, we maintain the temperature, let's say for example, or the heat to be 0. Okay? For all t. Right? Now, so in other words, now our problem becomes this. We want to find a u that will satisfy this equation, okay, as well as this equation, okay, as well as this equation or conditions. I say again, we want to find a u which will satisfy this one. This is the heat equation, as well as the initial condition, as well as the boundary condition. So all these must be satisfied. So that's what we want to find. We want to find a solution u of xt, okay, that will satisfy all these. Now, the method of separation of variables. If we want to use the method of separation of variables, what we do is that we assume, or we can let u xt to be a function of, to be a product of two functions f and g, where f is a function of x only and g is a function of t only. Okay, so of course there may be other forms of functions that we can use, but if we want to use the method of separation of variables, this is what we have to assume. That means we assume that this particular solution can be written as a product of two functions, one of which is a function of x only, the other one is a function of t only. And the strategy here is to apply these three steps. Okay, step 1, step 2, step 3. The first step is to apply the method of separation of variables like we would do to construct two ODEs. Okay, so the first one is to get two ODEs based on the fact that we are assuming u of xt is f of x times g of t. So that is step 1. Step 2 would be to solve these two ODEs by trying to satisfy the boundary conditions. Boundary conditions. Okay, we focus on the boundary conditions, find these two solutions to these two ODEs. And the last step is to then try and satisfy the initial conditions using Fourier series. That's where your Fourier series comes in. Okay, so get these three steps. So now we'll go through these three steps to solve. It's quite a long process and it may take us half an hour. Okay, so bear with me, we'll go through. So the first step The first step is to get the two ODEs, right? Okay, let's put down what we want to solve, which is du dt equals to c squared. This is what we want to solve. This is what we want to solve. So c is some real number. So remember this. Okay. So of course, our strategy is that we say let uxt be let uxt be a function f of x times g of t. Okay, then you see we need to then substitute this thing inside here, right? So we will need a du dt. Okay, so let's find du dt. What's du dt in terms of this and this? Now I'm going to use the dot notation for d by dt. So if I differentiate this thing, the right hand side, with respect to t, fx does not change, so it remains there. Okay, it's like a constant, and then g of t, I use the dot. The g dot means dg dt. G double dot will be d2g dt squared. So the dot is derivative with respect to t. Okay? And because I need a d2u by dx squared, I will have to differentiate u with respect to x twice. So for derivative with respect to x, I use the prime notation. So I will get f double prime of x times g of t. So far okay? Now, from this step on, I'm not going to put down f of x, g of t. So f means f of x. Capital F means f of x. Capital G means g of x. G dot means dg dt. F double prime means d2f dx squared. Okay? So now I'm going to substitute. So I substitute into PDE. If I substitute into PDE, what do I get? The left hand side I have f times g dot, right? Okay, and the right hand side I get c squared f double prime times g, right? Right? Then let's rewrite this. I'm doing separation of variables. Separation of variables means what? Put all the functions of one type, one variable on one side, function of the other variable on the other side, right? So if I were to do that, it will be something like f over f double prime. Okay, on one side, or maybe, sorry, I want the f double prime there. So let me write down as f double prime over f. Okay, equals to g dot over c squared g, correct? Am I right? Right? So what do I have here? The left hand side is a function of what? X only. The right hand side is a function of t only. If I have a function of x only equals to a function of t only, is it possible? Huh? Is it possible? Is it possible? Can you think of a function of x only that can be equals to a function of t only? 0, that's one possibility. What else? Constant. If I have fx equals to 1, is it a function of x? G of t equals to 2, is it a function of t? Yes, right? So the only way for these two, left hand side to be equals to right hand side, is when they are both, this one, both equals to a constant. Of course, f itself is a function of x. it may be some x something, x square something, sine x something. F double prime may also be some, but when you divide it out, when you take F double prime on F, it has to be equal to a constant because it is supposed to be a G dot over C square over times G. So the only way that this can balance is when it is equal to some constant. So far okay? Now the problem is that this constant, well, there are three cases. You mentioned 0. So this constant could be 0. That's one possibility. Or two other possibilities. What can it be? It can be positive. It can be strictly positive, larger than 0. Or it can be less than 0. So what we're going to do, so let me call this constant K. Okay, so if I call this constant K, like I said, K can be 0 or bigger than 0 or less than 0. Okay, it's quite long, so there are three cases. So let's go through all the three cases. Okay, so we will consider F double prime over F equals to K, right? So that means I have F double prime minus KF equals to 0. So this is my second order ODE in X only. Okay, so there are three cases. So case 1 is when K equals to 0. So when K is equal to 0, well, we only have F double prime equals to 0. Okay, which means that if we solve it, you get F is F of X. You integrate 2 times, right? Because this is equals to 0. You get what? AX plus B form, right? Now, remember what we wrote just now? We already split the step 1 we've already done. We've got 2 ODEs. This is one ODE. Where is the other ODE? The other ODE, I worry about it later. The other ODE will be G dot over C squared times G equals to K. But we'll worry about that later. So we have got one of the ODEs. Now we are applying the boundary condition. Okay. So boundary conditions. So I'm going through the cases, but applying the boundary. Somebody outside. But applying the boundary conditions now. So applying the boundary condition means that what are the boundary conditions? F at 0 equals to 0. F at L equals to 0. Why are these the boundary conditions? If you look at this is my boundary condition, right? This happens when S is equals to 0 and S is equals to L. But which means that we now substitute this inside here, and in order not to get trivial solution, because I have to set this to be 0 at this equals to 0, S equals to 0, and S equals to L, is either this equals to 0 or this equals to 0. If this is equal to 0, then for all t, you will get a trivial solution. So in order not to get a trivial solution, I must set these 2 equals to 0. Okay, which means that when you do that and you substitute inside here, you get A equals to 0 and B equals to 0, and you get a trivial solution anyway. So this case is not good. It will give us trivial solution. Okay. Let's look at case 2. Case 2 is when K is bigger than 0. If K is bigger than 0, let us make our lives easier by letting K equals to some P square. Easier to handle, right? Then you will have F double prime minus K, which is now P square F, okay, equals 0. Okay. So we will solve this. If you solve f double prime minus p square f equals to 0, what you're going to get, you can go and, actually you can do this, right? You use your characteristic equation, etc., right? Then you will probably think that you get e to the px, e to the negative px, correct? Yeah, but then if you express your solution as exponential functions, you find that it's harder to analyze. So what I'm going to do is I'm going to give you an equivalent solution in terms of hyperbolic function. It's the same thing, because hyperbolic functions can be defined using exponential, right? Right? What is cos x, for example? E to the x plus e to the negative x over 2. Right? So using that kind of concept, actually we can write down the solution of this particular equation using hyperbolic functions. And if we apply, say, the boundary condition f at 0 equals to 0, in fact, you will get a equals to 0, because sine 0 is 0, cos 0 is 1. Okay, so you will get a equals to 0, which means that now we can write down f as b sine px. And then we apply the other boundary condition, f equals to 0, and what you get is f equals to some constant b sine p times l. Okay, that's the left hand side, equals to 0. It looks promising, except that now we know that this term here is not 0 in general. Okay, therefore it also means that your b has to be 0. So what happens? You get a equals 0, b equals 0, you again get a trivial solution. So the case when k is equals to 0, you get trivial solution. K bigger than 0, you also get a trivial solution. So both these cases are not good. We are left with only the last case, case 3. Okay, hopefully this will give us some non-trivial solution. I don't know. Let's try. So the last case is when k less than 0. So again, make our life easier by letting k to be negative p squared. Right? Which means that now what we have is f double prime plus p squared f equals to 0. And if you recall the method of solving this second order ODE, straight away you can write down f will be a cos cosine, okay, px plus b sine ps. So very quickly, if you apply the boundary condition f at 0 equals to 0, what you get is that put x equals 0 here, this term disappears. Put x equals 0 here, cos 0 is 1. So I have a equals to 0. Okay, which means that now I can write down f is equals to b sine px. Oh, we better hope that b will not be 0. If b is 0, everything is trivial. We have no more choice. This is our last hope already. Right? Every case, and this is the last case, and this is our last constant. So what happens here is that if we let f at L equals to 0, the other boundary condition, that means we will have B sine PL equals to 0. Now, can this term sine PL be 0? Luckily for us, there are cases when sine PL is equal to 0. When is that? When does that happen? When does this happen? So your sine PL is equal to 0 when PL is some integer multiple of pi. Yeah. So in other words, if your P is chosen to be n pi on L, okay, then you will not get a trivial solution, because if your P is n pi on L, your sine PL will be sine n pi, right? Then that part will be 0, and your B doesn't have to be 0 in order to satisfy this boundary condition. Okay, so which means that if we choose the P to be of this form, that means earlier on we had that constant. If that constant is this, of course, if that constant is not this, we can't say anything. But if that constant is this, is such that that constant was K, right? If that K, which is equal to negative P squared, where P is this, we have a non-trivial solution, right? And the non-trivial solution will be f of x equals to some constant b multiplied by sine n pi on L x, right? Because this is my p. It's supposed to be b sine px, but I choose the p to be n pi on L so that my b will not be negative. But can you realize that actually there is an n here? So for each n, there's actually a bn, is a different bn, and for each bn there will be a different fn. So there are actually many, because if you choose my n to be 1, then f1 can be b1 sine pi over Ls. If this is 2, this will be 2, 2. There will be different constants, different coefficients, right? And so on. So, in fact, I'm going to put a little star down here on this B, because later on I'm going to use my B somewhere else. So, I'll put a little star here. So, these are actually my possible solutions for F. I haven't done G yet. G will come later, okay? I'm just finding, is it possible now for me to find F? Yes, and F must take this form. Correct? You see the logic that we have gone through? We split this up, right? We have got two. I have written one. I haven't written the other one. The other one will come later. So let's focus on this particular ODE first. I try to solve this ODE. But this ODE, I have 3 cases. So I go through the cases, and I find that case 1, I get trivial solution. So this equals to this constant, Jingyi, right? Just now, Qingyi, you mentioned could be 0. I'm telling you now, it cannot be 0. Because if it's 0, I will get a trivial solution. Then, you say it can be positive, right? Okay, let's try if it's positive. I also get trivial solution. So it cannot be positive. The only way is when this thing equals to a constant, and this constant is negative. And when I go through the analysis and so on, I find that if it is negative, then the F got to take this form. So now we have a form for one part of our solution. Remember, we want to find UXT, right? And we say UXT is F times G. We found F already. We found F.